Hey, this is a screencast on a topic that I find interesting. It's a topic that connects regression, or linear regression, to linear algebra. The context that we would find ourselves in statistics is if we're collecting data, and our data is bivariate data. So for each sample in our data set, we have two measurements. In this case, for the purpose of this screencast, I'm going to call those measurements xi and yi. We can visualize our bivariate data using a scatter plot, and I've got two scatter plots here on this slide. And sometimes our scatter plot shows that our data seems to want to fall into a certain pattern. In these cases, we can look at these and we can say, oh, these look like they're trying to be linear, and we can calculate what's called a correlation coefficient. If our correlation coefficient is exactly 1 or -1, then our bivariate data will all fall exactly onto a line. There will be no error, no deviation from that line. They'll all line up perfectly. If our correlation coefficient is close to, but not equal to, plus or minus 1, then we might say that our data looks like it's trying to fall into a line, and the closer the correlation coefficient is to plus or minus 1, the more successful that data is being. If we have a correlation coefficient that is close to plus or minus 1, we might want to know what is that linear relationship that the data seems to be trying to communicate to us. In this slide, you can see on the left, the data here looks like it's trying to fall onto this line, and it's pretty tightly grouped onto that line. And in fact, at the top of the plot, you can see the correlation coefficient is calculated and displayed there. It's about 0.98. Very close to 1. On the right, we have data that seems to want to fall into this downward sloping line, but it's more dispersed, it's cloudier. And look at the correlation coefficient there at the top, it's negative 0.798. So it's also close to -1, but it's not as close as the other data. Both of those data sets would benefit from having a regression line plotted, and I'll do that later in this screencast. Let's talk about how we find that regression line. Our textbook approaches that topic in a very analytic way. We identify the regression line by minimizing what's called a squared error function, and I'll show you that in a second. In this screencast, I want to show you a geometric way to look at this problem and a geometric way to identify that line of best fit. Both approaches will use an error function. So here's an error function that we're going to use. Notice what we're doing here is we're assuming, yes, there is a line of best fit, and that the y values do come from the x values in this linear fashion. So the error function is basically looking at the two different ways of getting the y values. One, using the linear function, and two, using the data that we were given. And in both of our data sets that we just looked at, you can see that those y values would be different. And so this difference here is going to be non-zero. Because the differences could be positive or negative, the approach is to square things so all these differences become positive, and so we don't accidentally have errors canceling out. So this is the squared error function that we're going to minimize. The line of best fit is the line whose coefficients, beta naught and beta 1, minimize this squared error expression. Our textbook tells us that the values of beta naught and beta 1 that minimize this squared error expression, and this is the same from the previous slide, have formulas given here. We won't use these formulas again in this screencast. These are formulas that are available in your textbook. The derivation of these formulas is tedious, it's not hard, uses a little Calc 1, uses some algebra, uses the definition of mean and standard deviation. We're not going to do it. If you look back at the formulas, you'll see they have a nice interpretation in terms of standard deviation and z-scores, something we haven't yet talked about. But what I want to focus on is the geometry that's hidden here. And just a reminder that if we have bivariate data, and the correlation coefficient of the data is not exactly plus or minus 1, the line of best fit will not pass through all the points in the data set. That's important for what's about to come. So in the language of linear algebra, finding a regression line for a big collection of bivariate data means asking for constants b and m, intercept and slope, that would make this line pass through all the data. That is to say, looking at this system of equations and asking for a solution is asking, is there a slope and intercept that would make a line that goes through all my x's and all my y's? I just reminded you that if our correlation coefficient is not plus or minus 1, there will not be such a set of parameters. So we're talking about an inconsistent system. So in the next few slides, I'll work through a couple examples of show how we quote-unquote solve this inconsistent system. And that quote-unquote solving will involve projection. So let's step away from statistics, step away from bivariate data for a moment, and just wade into linear algebra. And let's just talk about inconsistent systems for a moment. Here's a very simple system, a 3x1 system, or a system of 3 equations in one unknown. And we can abbreviate it with matrix notation, AX equals B. And just a reminder, X here is just a real number. It's a 1x1 matrix. This matrix only has a solution if this vector is parallel to this vector. There's lots of vectors in 3 space that aren't parallel to this vector, so there's lots of systems of this form that are inconsistent. So what if we have an inconsistent system and we need it to have a solution? What do we do then? A reasonable thing to do would be find that input x that gives us a vector that's closest to b. That is, find an x for which ax is as close as possible to b. So what we're going to do is we're going to look at the differences between all possible ax's and b and see if there's an x that makes this small. So to say we found the closest ax to b means that we've made this error the smallest. And we're going to call x bar the value that gives us the smallest error function, the smallest error value. So in our case, our 3x1 case, we can multiply out and find a formula for this error function. And here, using the distance formula, we do exactly that. And we get this expression, which you can note just by looking at it for a second, that it's a quadratic in x. It's a quadratic polynomial in x. Positive leading coefficient. It's a graph is a parabola opening upward, so we know it has a minimum. And so we can find we can use Calc 1 to find that minimum. So differentiate our error function, set it equal to 0, and solve. And so here's the derivative. Since the derivative is a linear function in x, it's easy to solve this equation, and there you go. Here's a diagram that shows us what's happening geometrically. We have the vector A, representing our matrix. Here the line, purple line, represents all the vectors that are multiples of A, so those are represented by AX. We have a vector here representing B. Because B is not parallel with A, our matrix equation, AX equals B, is inconsistent. Here in pink, we have the vector AX minus B. This represents our error. The length of this vector squared is our error function. As we vary x, this vector, the head of this vector, moves up and down the purple line. We want to find the x that gives us the shortest error vector. And we know that happens when our error vector is perpendicular to the purple line. So AX bar is this green vector. AX bar is also the projection of B into the direction A. So let's do another example. Suppose instead of a system with three equations in one unknown, we had a system with m equations in one unknown. This would change our error function slightly. The pattern is the same. The number of terms is different. If we rewrite the square of the distance function slightly differently and use the dot product of vectors, we get this expression, which again you see is a quadratic in X. And A transpose A is a positive number, so this is the graph of this would be a parabola opening upward, so it has a minimum. We can find that minimum by taking the derivative and setting the derivative equal to 0, and then solving for X. And there we get X bar, the X value that minimizes our error function, and it has this formula. Again, if you look at that, you'll see that this formula looks a lot like our projection formulas that we learned in linear algebra. Now let's make this a little more complex. Suppose we had 2 unknowns and 3 equations. Then A would be a 3 by 2 matrix, and let's assume that its columns are linearly independent. So its column space is a plane. Now remember that A times Y, where Y is a vector, this is just a linear combination of the columns of A. So saying that AX equals B is inconsistent means that B is not in the column space of A. That means that B can't be written as a linear combination of vectors, or the column vectors of A. So the next diagram is going to show you what that might look like geometrically. So here we have the vector representing the first column of A. Here we have a vector representing the second column of A, and they're drawn so they're linearly independent. Here we have a vector representing A times X. It's a vector that's in this plane, so it's a linear combination of these two vectors. Here we've got our vector B. It's outside the plane, so it's not a linear combination of these two vectors. So the matrix equation AX equals B is inconsistent. Now the red vector here represents AX minus B, which is the error vector, and its length squared is our error function. So as I change X, the tip of my vector moves around in the plane, and that changes the red vector. And we want to find the value of X that minimizes the length of the red vector. And we know that right here, as pictured, the green vector, this represents the error vector that minimizes or has minimal length. And you can see it's perpendicular to the column space of our matrix A, and it is the projection of the vector B onto the column space of A. So geometrically, once again, we see projection is the key to understanding what's going on. So these two examples suggest that the error vector, AX minus B, is minimized when AX is a projection of B onto the column space of A. So this happens when AX minus B is orthogonal to the column space of A. So geometrically, that means that AX minus B dotted with AY is 0 for all Y, because AY is a linear combination of the column vectors of A. So we'll come back to this in a minute. Let's jack this up one more time. Suppose we have an inconsistent system of M equations in N unknowns. So let's find the projection of B onto the column space of A. For any Y in Rn, AY is in the column space of A, right? It's a linear combination of the columns of A. So we're looking for an X bar in Rn for which AX bar minus B is orthogonal to the column space of A. That means AX minus B dotted with AY is 0 for all Y, for all linear combinations of the columns of A. So using properties of the transpose, we can rewrite this as this. If Y dot this is 0 for all Y in Rn, then this must be 0. So that leads us to this expression. And this leads us to the main result in linear algebra as it pertains to regression. The least square solution to an inconsistent AX equals B of M equations in N unknowns satisfies this equation, which we saw in the previous slide. If the columns of A are linearly independent, then A transpose A is invertible, and so you can solve uniquely for X bar by multiplying both sides by the inverse of A transpose A. And this vector is exactly the projection of B onto the column space of A. In the context of regression, we're going to be using this matrix to find the coefficients of a line of best fit. So back to statistics. When we have a bivariate data set, and the set of points in our data set have a correlation coefficient that's not equal to plus or minus 1, we might want to find the line of best fit. That means we're looking at a linear system like this that's inconsistent. So our coefficients, beta naught and beta 1, can be found using this matrix equation. Luckily for us, we don't have to do those calculations by hand whenever we want to find a line of best fit. We can go to our R software. So suppose we have bivariate data where the variable var1 represents all the x measurements and the variable var2 represents all the y measurements. We can find the regression line for that bivariate data using this command right here. LM stands for linear model. So we put the dependent variable first, and you put a little tilde, and then you put the independent variables next. It's a good question. What happens if you get them reversed? That's a good question to think about. If you want to see the coefficients that are generated by R, use the command coefficients and put your command inside that, and R will show you. If you want to work directly with those coefficients, maybe give a name to the linear model you create. Then you can execute coefficients and put in this case I said fit. And here if you use the square bracket 1, it'll tell you what the value is and what the name is. In this case it's going to be the intercept. But if you only want the number, then you have to put a double square bracket. If you want to plot the regression line along with your data, first plot your data, and then use this command. So AB line coefficients fit. The AB line is a command that will say, give me a slope and intercept, and I'll plot the line. And that's exactly what this command does. And here I'm just going to color that regression line red. So here's a command for generating some bivariate data with a high correlation, and then compute its regression. Here I'm generating some x coordinates, 50 measurements in fact. Here I'm generating some y coordinates using those x coordinates. Then I'll calculate the correlation coefficient, and it will not be 1 or -1. I'll plot the points, create the linear model, the regression line, and then plot the line along with my data. What happens is once I plot this, if I execute this command after the plot, it'll add this to that plot. So there we go. That's what we get. There's my data from the first slide along with the regression line. Here's the code for generating the second example that started out this screencast. And here's the regression line that goes along with it. So now you understand a connection between regression and linear algebra through projection. This is fascinating to me. I hope you find it equally interesting. And I hope you find the R commands at the end of the presentation useful.